Welcome to this explainer. If you're the kind of person who just loves to understand exactly how the world works, right down to the literal nuts and bolts, you are in the perfect place. Today, we're focusing our attention on an absolutely crucial yet almost entirely hidden piece of engineering: railway track fastening systems. Most of us, we look at a train track and we just see steel and concrete, right? But the real magic, the actual technology that guarantees railway safety, is the system that holds those two elements together. I really want you to imagine the staggering mechanical stakes involved here. Picture a massive train, weighing hundreds or even thousands of tons, just barreling down a railway line at top speed. The dynamic forces generated by that kind of moving mass are almost unfathomable. So what actually keeps that train from literally ripping the steel tracks completely off the concrete base below? It's definitely not just gravity. It requires a highly engineered, rigorously tested mechanical solution. Okay, let's dive into this. Track fastenings essentially act like the ligaments of the railway. Every single time a wheel axle passes over, the rail is subjected to just an intense combination of forces. We're talking vertical crushing loads, lateral side-to-side forces, rotational twisting in literally both directions, plus longitudinal pushing and pulling from thermal expansion and traction. The fastening system has to endure all of these high dynamic stresses, basically absorbing the punishment while keeping that steel rail perfectly anchored. So here is our roadmap for today. We'll start with the railway fastening problem, then defining modern fastening systems. After that, rigorous testing and standards, followed by the two modern contenders, and finally, the financial payoff. Let's start with Section 1, the railway fastening problem, and really the limits of the legacy system. So, for nearly half a century, major networks like Indian Railways have relied on traditional elastic fastening systems. But as you can probably guess, as trains get heavier and a lot faster, those limits get pushed to the breaking point. When you look at legacy elastic rail clips, specifically the ERC Mk-III and Mk-V, you find a major flaw. Because of their geometry, specifically a sharp reduction in diameter at the leg, they suffer from intensely high stress at what engineers call the transition zone. This creates differential hardness, leading to severe breakages. Add a little moisture into the mix, and these clips heavily corrode, which causes a highly dangerous loss of toe load, which is just the engineering term for the clamping force keeping the rail safe. But the problem isn't just about the metal, it's honestly philosophical. The old way of doing things meant buying individual parts. You'd get clips from one vendor, liners from another, pads from a third. And because each component comes with its own tiny manufacturing tolerances, when you put them all together, those tiny deviations stack up. This tolerance stacking frequently results in clips that either overdeflect or underdeflect, which radically reduces that critical clamping force. The modern approach completely changes this by demanding single-point responsibility. That means one single source designs and supplies the entire cohesive fastening system. Everything is built to work in perfect harmony. Which brings us right to Section 2, defining modern fastening systems, and that crucial concept of single-source responsibility. So if we're transitioning away from that patchwork approach of the past, what exactly are we looking at now? If you're asking, tell me about the newer modern fastening systems. Here is the core definition. It's a comprehensively designed assembly. It doesn't look at the rail, the pad, and the clip as just isolated pieces of metal and rubber. No, it treats them as a unified, high-performance ecosystem. The whole focus here is on improving the overall clamping force, drastically increasing the fatigue limit so the parts don't just snap under pressure, reducing installation costs, and above all, taking full, single-source responsibility for how the system actually performs out on the tracks.
Let's move to Section 3, rigorous testing and standards. This is basically the trial by fire.
Now, what's really interesting about this slide is seeing the brutal European standards, known as EN 13481, that these modern systems have to survive before they ever see a main line. First up is the longitudinal rail restraint test. Rails naturally want to expand, contract, and creep. That's just what happens with intense thermal changes and the massive tractive pulling forces of a train engine. Modern systems are tested to ensure they provide a minimum longitudinal restraint of 7 kilonewtons. This is incredibly important because it optimizes the breathing length of long-welded rails. Without this, you could get massive, dangerous gaps forming if the rail were to fracture. Next up, we have the attenuation of impact loads. For this test, they literally drop a massive weight directly onto the assembly. Why?
Well, it proves whether or not the modern rail pads can successfully dampen severe vehicle-induced vibrations. Think about it. If a fastening system can't absorb those dynamic impacts, the entire shockwave transfers directly into the concrete sleeper below, which causes it to crack and fail way before it should. These modern pads are specifically engineered to act as heavy-duty shock absorbers.
And then we have the granddaddy of them all, the repeated loading test. The fastening assembly is subjected to a staggering 3 million cycles of repeated loading. It's designed to simulate years and years of heavy train traffic. The scale of this test is just hard to overstate. And here is the real kicker. After enduring all 3 million of those punishing cycles, the system's clamping force cannot change by more than 20%. Basically, if it loses its grip, it fails. No exceptions.
All right, Section 4, the two modern contenders, the Vossloh W-30 and the Pandrol FE-1504.
So it's time to actually look at the real-world hardware. Let me introduce you to the contenders that actually survived those grueling tests. On the left, we've got the Vossloh W-30, and on the right, the Pandrol FE-1504. Just looking at them, you can instantly see the massive leap in engineering compared to those rusty, broken legacy clips we talked about earlier. These are incredibly sleek, highly optimized designs. And they aren't just theoretical either. These exact systems are already battle-proven on major heavy-haul railways across the USA, Russia, Europe, and beyond.
And this brilliantly illustrates the shared advantages of these systems. Both the Vossloh and Pandrol setups are packed with high-tech features. They both perfectly comply with those brutal Category C European standards we just looked at. They fit flawlessly into conventional ballasted tracks. They both use an innovative linerless design which completely removes one of the absolute weakest links of the old system. They even have built-in anti-vandal mechanisms, and maybe the best part, if a component does happen to wear out, it can be entirely replaced without having to dig up and change out the massive concrete sleepers. That drastically reduces ongoing maintenance. Let's wrap up with Section 5, the financial payoff. We're looking at a 30-year life cycle cost analysis. Now, upgrading thousands of kilometers of track is obviously a massive logistical undertaking, but let's look at the actual data here. Notice the initial procurement cost. Yes, it's higher for the modern systems, over 10.2 million rupees per kilometer for Vossloh and over 10.5 million for Pandrol, compared to about 6.2 million for the old system. But look closer at that traffic block cost row. Because the old systems fail constantly, fixing them seriously disrupts train traffic, which costs over 6.1 million rupees in delays. The modern systems practically eliminate this issue entirely, plummeting that block cost down to just over 193,000 rupees. It is literally night and day. When you tally it all up over a 30-year lifespan and you deduct the scrap value, you get this very bold number, 3,930,023 rupees. That is the massive total net savings per single kilometer of track when switching from the legacy system to the modern Pandrol system. When you multiply that by thousands of kilometers of a railway network, the savings are just astronomical. It absolutely proves that investing upfront in superior modern engineering ultimately pays for itself. I want to leave you with this final, forward-looking thought directly from the engineering analysis. It has become inevitable to go for a proven, modern fastening system supplied by a single source. We really can't afford the physical or financial breakages of piecemeal legacy designs anymore. Standardizing to a highly tested, single-source modern system isn't just a nice option. It's the only viable path forward for securing global rail infrastructure. Thanks so much for joining me on this explainer. It really does make you wonder, right? If this much cutting-edge engineering is hiding in the simple tracks right beneath a train, what other invisible infrastructure out there is quietly keeping our modern world running, just waiting for its own upgrade?